Hi, welcome back. So, this is the third in the series of our machine learning sessions. In the past, we learnt about prediction and specifically time series prediction using auto-regression and moving average techniques, and we also learnt about autocorrelation function and partial autocorrelation function as to how they help in determining the order P and the order Q. There is another important concept when we are trying to use autoregression and moving average techniques. So there is an important concept of stationarity, or in simpler terms, a stationary time series. So this AR and MA algorithms assume or make a fundamental assumption that the time series that we are trying to model is stationary. And what is the meaning of stationary? That's what we have to understand. So let's say if we take a time series, and this is my time axis and this is some y value, and let's say this is my center value 0.5, and this is 0 and this is 1, and I have values something like this. If you take a closer look, even though the values are reaching here or going down, it looks like the average value settles at around this point, as compared to another time series where if it is like this, it seems that on an average the time series values are increasing with time. Now, this series where the mean is around a value irrespective of which time slot we choose, either this or this, the mean is generally centered, or the values are oscillating around a value, vis-a-vis this one where it just keeps increasing. So if I am analyzing in this slice of time, the values are between these two. If I analyze in this slice of time, all the values lie between these two. So this is different from this value. That is the simplistic concept of a stationary time series. So this time series is called stationary, and this one is not stationary. Now, when we are using AR or MA techniques, our input time series must be stationary. That is the fundamental premise on the time series in which we are trying to run prediction. Now, let's get a little deeper into the understanding of why stationary. Now, one thing I have not understood, or probably I have not figured out the answer yet, is why they are assumed to be stationary. But for now, understand that the time series must be stationary. So let's say the time series is y is equal to alpha y t minus 1 plus the error term. Now, if the value of alpha, the modulus value, absolute, is less than 1, then this time series would be nearly stationary as compared to alpha being 1 or greater than 1, meaning the equation could look like yt minus 1 plus the error term. So if this condition is satisfied, this one would be stationary and this one would not be stationary. So let's figure out through a Python code. Okay, let's understand the graphs by using Python. So remember, we said this equation y is equal to alpha previous value of y plus some error term, which is a random value. Generally the mean would be 0 and with a variance and standard deviation, vis-a-vis this one where alpha is equal to 1. So remember, y is equal to previous value of y plus an error term, and in terms of stationary, the value of alpha is less than 1, whereas anything that is not stationary, the value of alpha is 1 or more. So let's plot this and see how it looks like. So you will have a few imports to help us. I plot plt, perfect. So now let's create the y values. Let's start with just look at how random number plot looks like. So we have plotted 100 random numbers, and so therefore we need 100 x values. And let's plot this. Plt dot figure, fig size is equal to, then t dot plot x and y. Sure, let's see. Perfect. So if you see here, the values are from 0 to 1. However, on an average, they should be centering around 0.5. So let's see what is the mean of the values. Mean, I think it's called average y, and then let's print the mean. Yes, it's about 0.53, so it's hovering around 0.5. Now visually looking at it, it is clear that all these values are either above 0.5 or below 0.5, and they are hovering around that number. So this should ideally be a stationary plot, because whichever time slot we choose, our average should be around 0.5, which will not change. Now let's construct the equation. Remember, we have the current value of y here, this one is equal to some constant alpha multiplied by previous value of y and a random number. So let's make alpha as 0.2, and let's say we start with the value of previous value of y with 1, and here is my series, and I will have an array to store the series. Now let's compute for 100 values. So for step in range 0 to 100, so I will do this 100 times. I want to compute y, which is equal to alpha multiplied by, remember this equation, alpha multiplied by previous value of y. So previous value of y is y0 plus this error term, and I'm using random, so I'll get a random number. Then I will store this value in my series. So this is the computed next values of y, and then now for the next y, my current y becomes y0, or the previous y. So y0 should be equal to the new value of y, and it will be done 100 times. Let's see what happens when we plot this. plt.plot, and I want to plot the x against series. Sure. Once again, this looks like the mean is approximately 0.5. Let's compute and see if that is truly the case. This time I'm computing the mean of the series, and yes, it is about 0.6, 0.5, somewhere around that. Can I change alpha and I will reduce it, let's say, and see what is the mean value? It should still be, yeah, it is still around 0.5. And the series looks truly random, where whenever the value goes above 0.5, at some point it is pulled below, and then when it goes way below, 0.5 it's pulled up and it oscillates. This is a stationary time series. But as alpha starts to grow, this behavior of points in this time series trying to stay closer to the mean value will start to deviate. So now I've moved alpha up and made it 0.8. Now you see that there are longer periods in which the value stays way above 0.5, or the mean value in this case, 2.5, because the values are now between 1.5 and 3.5. So mean would be about 2.5, 2.7. Yeah, this is what it's saying. And then if you see, there are areas where the values consistently stays above. If I still move it further to 1, now this is an increasing graph. The mean has no meaning here because the mean keeps changing when I keep, when I actually look at different, between 20 and 40, 40 and 60, the mean values are different. So this is non-stationary, whereas alpha closer to or less than 1 will give me stationary values. The more closer to 0 it is, the more random it is, because if it is alpha is 0, this equation, if you see, is truly a random number. So if I make it 0, this curve that I will get will be no different from the previous curve that we got using the random numbers. So if alpha, and we can do actually a negative value also, so minus 0.3, if I do, I will still get a stationary series. But as alpha tends to 1, 0.9, you will see series losing its property of being a stationary. That is the difference between a stationary series and a non-stationary series. To reiterate, if you want to use AR or MA methods, the time series that you are using to build your model should be stationary. If it is not, then you will not get a model that's accurate enough. So with this, I hope you've understood the concept of what is a stationary time series and what is a non-stationary time series. There are two more important concepts that we need to understand. One is called null hypothesis, hypothesis, and the other is called unit root. In very simple terms, hypothesis everybody understands. It's making a statement which may be true. So null hypothesis states that if there exists a unit root, again to simplify, for an equation like this, there might be a case where when you solve for this, alpha becomes 1, and when that happens, as we have seen in the Python plots, it is no longer stationary. So null hypothesis states that there exists a unit root for the equation, therefore the equation is not stationary. So our objective is to find equation where we can continue to reject this null hypothesis, or alternatively where there is no solution, no unit root, where the equation becomes non-stationary. We do that using something called Dickey-Fuller test or augmented Dickey-Fuller test, and this is the subject of next video. If you feel the concepts are not clear, there's some error, or I need to improve this, please mention it in the comments below. Thank you. Bye bye.